In this module, we will demonstrate the results that we have theoretically developed earlier. That means, with the help of a data set, we will show the equivalence between expressions involving simple, partial and multiple correlations, and also the estimates obtained from the multiple regression model and estimates obtained from the simple regression models. And finally, we will generalize these results through the help of a theorem called Frisch-Waugh-Lovell theorem. In this module, we will demonstrate the results that show the relation between simple, partial and multiple correlation with the help of a small data set. So, this data set contains y, x1, x2 and x3, and we will use this data set to obtain some results, which we will now insert or substitute in the formula which have already been explained and discussed in the previous module to come out with the results. So, let us get started. So, the data set is made up of columns 1, 2, 3 and 4. So, these are the values of y. x1, if you recall, is the variable associated with the intercept. So, it is always 1, x2, x3. So, first what we do is we find the totals. The totals are also worked out, and there are 1, 2, 3, 4, 5 observations. So, the mean is 20 divided by 5, 4, that is 5 divided by 5 is 1, 15 by 5 is 3 and 25 by 5 is 5. Why we do this is, as you recall, it is easier to handle the regression in terms of deviation. So, these small letters are variables in deviation. So, from y we subtract the mean to obtain this column. Small y is y minus y bar. Similarly, small x2 is x2 minus x2 bar. x2 bar is 3. For example, this is 1 minus 3 is minus 2, 5 minus 3 is 2. And easy way to check whether your results are correct is, if you add up the variables in deviation form, then summation small y, summation small x2, summation small x3 should all be 0. So, that is the check. And then we need these values y square, x2 square, x3 square, x2 x3, y x2 and y x3. So, from the variables in deviation form we compute these values, and the summations are all given in this row. Next, what we do is we recall the formula for simple correlation coefficients between y and x2, y and x3 and x2 and x3. Then we also recall the formula for partial correlation between y and x2 given x3, and similarly partial correlation between y and x3 given x2. So, that gives us simple correlation coefficients and partial correlation coefficients, and finally the relation between simple, partial and multiple correlation is given as this first part. If we first introduce x2 and then go for x3, then this is the stepwise decomposition or stepwise development of the total sum of squares into explained sum of squares and residual sum of squares. Or if we first introduce variable x3 and then go for x2, then this is the formula r square y3, because first y3 r square y3 because first x3 has been introduced, then x2 has been introduced, and correspondingly the residual sum of squares are also composed. What we all just need to do is to substitute these values. For example, yi x2i is nothing but this summation 16, summation yi square is nothing but 28, summation x2i square is nothing but 10. So, why don't you try it out, and in a few seconds you will be getting to know the results that you will obtain by substituting these values. So, please take a look, please try out and then take a look at the results. already taken a look at the relation between multiple, simple and partial correlation coefficients. We now want to compute separately the multiple correlation coefficient and the square of that, and for that we recall that r square y dot 23 is nothing but explained sum of squares, this beta 2 hat summation y x 2 I plus beta 3 hat summation y I x 3 I all upon total sum of squares. These things we are already familiar with from our previous modules. So, we need to compute beta 2 hat and beta 3 hat. For that we recall the normal equations, that is x prime x times beta hat is equal to x prime y. This will solve for beta hat. So, what is x prime x? Please remember that x prime x is given by the matrix summation x 2 I square summation x 2 I x 3 I and again summation x 2 I x 3 I, finally summation x 3 I square. So, this matrix is x prime x and beta hat is a vector represented as beta 2 hat and beta 3 hat. So, this is a pair of simultaneous equations. So, if we solve this pair of simultaneous equations, we come out with the result that beta 2 hat and beta 3 hat are given as 2.5 and minus 1.5. Why do we do this? We do it so that we can insert beta 2 hat here, beta 3 hat here, and summation y x 2 is already given here, which is 16, summation y x 3 is already given here as 9. So, we find the numerator and the denominator is also present here, which is summation y I square, which is equal to 28. So, substituting these values here, the result that we obtain is r square y dot 23, that is the coefficient of determination or the square of the multiple correlation between y and both x 2 and x 3 on the other hand, is given as 0.9465. So, what is the interpretation of this? It means that 94.65% of the total variation in y is explained by the variables x 2 and x 3. So, 94.65% is explained by x 2 and x 3, and the balance is, you might have guessed already, the balance is the residual sum of squares. So, 100% minus 94.65 is about this is 0.35 and that is 95. So, that is 5.35% will be the residual sum of squares. These results, dear viewers, will be presented in the ANOVA table that will just follow. Viewers, now we will take a look at the computations from the data that will show the relation between the regression coefficients obtained from the multiple regression on the one hand and the regression coefficients from the simple regressions on the other hand. So, these formula are already familiar to you. Beta 2 hat is the coefficient of x 2 in the regression of y on x 2 and x 3. So, basically it is beta y 2 beta hat y 2 minus beta hat y 3 times beta hat 3 2 divided by 1 minus r square 2 3. Similarly, beta 3 hat is beta hat y 3 minus beta hat y 2 times beta hat 2 3 divided by 1 minus r square 2 3. And how do these simple regression coefficients work out? Beta hat y 3 is the estimated regression coefficient when y is regressed on x 3, that is summation y I x 3 I divided by summation x 3 I square. Similarly, beta hat y 2 is y x2 summation divide x2 square summation, and beta hat 2 3 is the regression coefficient when x2 is regressed on x3. So, you have x2 and x3 on the numerator and x3 square in the denominator. Finally, beta hat 3 2 is the regression coefficient estimated when x3 is regressed on x2. So, you have x3 and x2 square in the denominator. All that we need to do is to substitute these values. For example, summation yi x3i is 9 divided by summation x3i square, that is 4, so on and so forth. So, once we obtain beta hat y3, beta hat y2, beta hat 2 3 and beta hat 3 2, that means once we obtain the simple regression coefficients estimates, then we can substitute those values in the first two formula to obtain beta 2 hat and beta 3 hat. And guess what? We have already shown that beta 2 hat would come out to be equal to 2.5, whereas beta 3 hat would come out to be minus 1.5. So, why don't you go ahead and make these substitutions to obtain the simple regression coefficients, and second, substitute back to the formula for the multiple regression coefficients and check out, you will get these results. And to corroborate that, you will be seeing the slides that show the workings in a few seconds. Specifically on the relation between the regression coefficients obtained or estimated from the multiple regression model and from simpler regression models. So, we will take a look at the basic idea behind a theorem called Frisch-Lovell theorem, and let us get started. So, we have our multiple regression model as y is equal to x beta plus u. Please note that this is the k variable model. So, this is n observations, the order of x is n rows and k columns, and the order of beta is k cross 1. So, we have beta 1, beta 2 right up to beta k, and this u is also u1, u2 up to un. When we estimate this model, viewers, you already know that the estimated relation is x beta hat plus e. So, beta is replaced by its estimate, and therefore, the relation is not exact. So, there is an error. So, that is the error vector. Now, what we will do is we will see how to obtain a subset of this beta. For example, if there are 7 betas, beta 1 up to beta 7, then how to obtain just say beta 3, beta 4 and beta 5, something like that. Before that, some preliminaries. So, we know that beta hat is given as x prime x inverse x prime y. So, we replace beta hat by our known formula, that is x prime x inverse x prime y, and therefore, the error is y on the left hand side minus this first term on the right hand side, which is x into x prime x inverse x prime y, which gives us I minus x into x prime x inverse x prime y. So, that is apparently a formidable expression, but it is very simple. So, you take y common, so that you have I minus x into x prime x inverse x prime y, and that we denote as m times y. So, this matrix M is called the residue creating matrix. Why? Because if you pre-multiply y by M, then you get the residual vector. So, this M is the residue creating matrix, and the property of M is this M matrix is symmetric as is very clear. If you take the transpose of this, you get the same thing. So, it is symmetric and it is also an idempotent matrix. That means, if you multiply this by itself, m into m gives m again, that is m square is equal to m. Further, two more important properties of the residue creating matrix are as follows. So, if you write m times E, dear viewers, then you multiply this with E. So, that is E, instead of y you have E, and then you have x into x prime x inverse x prime E. You all know that x prime E is equal to 0. That is basically the compact way of writing the normal equations. These were elaborated in the earlier modules. So, m times E is equal to E, and finally m times x, if you multiply this with x, then you have x here, and x prime x inverse gives the identity. So, x minus x is 0. So, M, the residue creating matrix, is a symmetric idempotent matrix. That means m square is equal to m. Further, m E is equal to E, and m times x is equal to 0. We will now use these properties to split this beta vector into two components. One may be from the first to the third, and the second may be from the fourth to the seventh, and we will see how to obtain one set of betas from this relation. So, viewers, we now write down the multiple regression model by splitting the x variables and the corresponding betas into two components. So, the x matrix is x1, x2, xm, and then m plus 1, m plus 2 up to k. So, the first set of m variables we denote as x1 with a bracket, and the remainder we denote as x2. So, that gives us x1 beta 1 plus x2 beta 2. Please note that this is a set of x variables, this is another set of x variables, and the estimated relation is given when we write, instead of beta 1 hat, instead of beta 2 hat, and we have this error. So, what is the basic idea? If you want beta 2 hat only the betas associated with the second set of variables, then how do we go about it? What is the general principle that we had already discussed and elaborated? Basically, we will cleanse y of x1 and obtain pure y, then we will cleanse x2 of x1 and get pure x2, and then we will regress pure y on pure x2. So, first y will be regressed on x1 and the residuals will be obtained, and then x2 will be regressed on x1, the residuals will be obtained, and the final result is as simple as saying that we obtain beta 2 hat when we regress pure y on pure x2. Now, it will turn out to be that we will not have to go through such an elaborate procedure, only the first part will be enough to give us the final result. So, we begin by regressing y on x1 only and getting pure y. So, that is written as y is equal to x1 beta 1 hat plus an error when y is regressed on x1. Because this error and this error are not the same, here you have only x1, here you have x1 and x2. So, what is this beta 1 hat? This beta 1 hat is going to be x1 prime, x1 inverse, x1 prime y, and therefore, this y will be equal to x1 times beta 1 hat, which is x1 prime, x1 inverse, x1 prime y, plus E when y is regressed on x1. Therefore, this residue y regressed on x1 or pure y will be I minus x1 into x1 prime x1 inverse x1 prime y. That we now denote as M1y. The same principle, y regressed on x1, so that is the residue creating matrix M1. Only instead of x, we have x1 here. So, that is the residue creating matrix. So, that is nothing but pure y. Of what use is this? Let us see how we can use this. So, from this basic relation, we can write M1 times y. From this first or original relation, we can write M1 times y is equal to M1 x1 beta 1 hat plus M1 x2 beta 2 hat plus M1 times E. Now, let us recall the properties. Remember, m into x was 0. So, M1 times x1 will vanish. This is 0. What else? Remember, m times E was E. So, this will also be equal to E. So, this reduces to M1y is equal to M1 x2 beta 2 hat plus E. Now, we will come to the final result in a single step. What we simply do is we pre-multiply by x2 prime. So, x2 prime M1y is equal to x2 prime M1 x2 times beta 2 hat plus x2 prime E. And once again, from the normal equations, x2 prime E must be equal to 0, because x prime E is one whole set, a part of which is x2 prime E. So, both these are equal to 0, x1 prime E and x2 prime E are both equal to 0. So, this is equal to 0. That, dear viewers, leads to the final step, that is x2 prime M1y. So, we have x2 prime M1y is equal to x2 prime M1 x2 beta 2 hat. So, what is this? This is nothing but x prime x when x is replaced by x2 purified of the effect of x1. So, therefore, beta 2 hat is x2 prime M1 x2 inverse x2 prime M1 y. And if you further explain it, I mean if you further elaborate on it, it is very easy to see what is this x2 prime M2 prime or M2 x2 prime M1 x2 prime M1 x2. Just take a look at the first component. This is like x prime x inverse. What is x here? It is x2. What kind of x2? x2 purified of the effect of x1. So, M1 is the residue creating matrix. So, this is pure x2 prime pure x2, pure x2 prime pure x2 inverse. And what is this? The second component is x2 prime M1, and again, or rather you can write it as M1 x2 prime M1 y. What is M1 y? It is pure y. What is M1 x2? Pure x2. So, this is like x prime y. What is this x prime x inverse? What is this x prime? It is x2 purified of the effect of x1, because you are pre-multiplying with M1, the residue creating matrix. So, how did you get beta 2? You got beta 2 by regressing pure y on pure x2. So, that is the generalization which gives us the result that beta 2 is the coefficient obtained by regressing pure y on pure x2. So, that, dear viewers, is a generalization of the results that we have been discussing about. That is, when you want to obtain beta 2, what you do is you obtain pure y, take out the effect of x1, and then you take x2 and regress on x1, take the residual, that is pure x2. Finally, you regress pure y on pure x2. It is just like x prime x inverse x prime y, only this is pure y and this is pure x2. So, viewers, with that we come to the end of this module, which discussed the relationships between simple, partial and multiple correlations with the help of data, and the generalization of this result, which is called the Frisch-Waugh-Lovell theorem.